Invitation. Thank you. Thank you for coming. Okay, let's see. I got a recording note here. Let me continue. Okay. Today I'm going to talk about the clouds and the hazes, basically the lifted particles in the atmospheres. I assume everyone comes in very diverse backgrounds. Some studying Earth atmosphere, some studying atmospheres of other planets. And we all know clouds are very important for the Earth climate. Okay, it's one of the biggest uncertainties preventing us from precisely predicting future climate. But also, as I'm going to show today, clouds and hazes particles, although they're little, they play important roles in almost every atmosphere on planets. Inside the solar system, outside the solar system is a lot of interesting things we can discuss. Okay, and first, just give us a very simple introduction, okay, by showing beautiful pictures of different planets, including the air pollution picture on the left, upper left panel. Okay, this is Los Angeles with a lot of SOAs, secondary organic particles, aerosols from the air pollution. But as I said, the particles are basically ubiquitous in every atmosphere we point outward the Earth. For example, one of the very important examples of the haze is Titan haze. This second panel here, you can see my laser pointer. There are two kind of haze layers. Well, there are actually numerous haze layers in Titan's atmosphere, but you can see very clear there's detached haze layer, which is about like 500 kilometers above the surface of Titan. Okay, Titan looks like an orange ball from outside because of those organic hazes. Okay, and they blocking the light. And the right upper image is Pluto. Okay, this is this spectacular image is from the New Horizons mission from NASA, and during Pluto flyby in 2015. And you can see, although Pluto is a very small dwarf planet, it's not even a planet, right? But it has a very thin atmosphere with atmosphere pressure about 1 Pascal. And you already got a lot of haze layers, numerous haze layers, okay. A lot of interesting things going on. We can talk about that. And our sister planet, Venus here, and this is the UV image of Venus. And the first, if you just look at the visible images, you can see Venus is covered by clouds. And if you look at UV images, there are some like dark stuff inside the clouds, which absorbing the blue and UV light, okay, which we still don't know what are they. So we have a lot of those kind of particles, like big clouds, okay, covering the whole planet, and some like interesting stuff, perhaps also in the solid and liquid phase, absorbing the UV and blue light. And we got beautiful plumes, okay, dust plumes with some like water ice cloud shaded in blue on Mars surface. Okay, and here you can see clearly the gray red spot of Jupiter. The red is, okay, the red color comes from some particles. We don't know what they are. We have some candidates, and white ovals and white banded stuff, and with brownish bands. All of those come from cloud colors. Okay, and though I'm not going to the rest of it, but I just want to say, okay, those clouds particles are pretty common, okay, in the solar system planets, which we do have very clear images to show their evidence. And today I'm also going to show even for distant exoplanets, exosolar planets, we do not have resolved images, but we do find strong evidence there are clouds, there are particles in their atmospheres that play important roles in their climate. All right. So one very simple question, okay, is, how do we categorize those kind of these kind of particles inside the atmosphere? A simple one would be to think about their sources, right? There are like two kinds of sources, as I said, briefly mentioned before. One of them is secondary organic aerosols you can think about on Earth, right? So they're photochemically or chemically produced by gases in the atmosphere through very complicated chemical reactions. And then they coagulate and the sediment grow, become big and suspended in the atmosphere. And they're called photochemical hazes, okay? And the other part is the other kind of category of particles. We can call it condensed clouds, or you just call it clouds. This is a very common you see on Earth. And basically you have thermodynamics working there, right? And once you got vapor basically exceed the supersaturation, okay, see the saturation vapor pressure, you will condense, okay, and doing the phase transition, and the water clouds forming that way. Okay, I'm not saying one planet should, more dominated by hazes, other planets are dominated by clouds. Usually they have multiple interactions between the hazes and clouds as well, okay, but they have very different origins. So do keep in mind, you think if you produce this kind of hazes, they produce in the higher upper atmosphere. And if you produce this kind of clouds, the gas has to be dredged up from the bottom, right? So they might have very distinct layers and play different roles in planetary atmospheres. And if we go beyond Earth, we are no longer think about the water clouds, okay? In fact, we have a lot of possible candidates. This is a very busy plot. I apologize, but this is what nature is, okay? This, if you look at the color lines, those are temperature profiles as function pressure for different planets inside of the solar system and outside the solar system as well. And you can see I try very hard to put Pluto and Triton atmosphere on the upper left corner because they have very thin atmosphere, but we do have very thick atmosphere like Jupiter. We have very cold atmosphere like Neptune and Uranus, but we have very hot atmospheres for hot Jupiters or even hot planets, okay, ultra hot Jupiters. And those dashed lines are basically condensation curves of different kind of species. For example, ranging from nitrogen does condense, okay, in Triton's atmosphere, for example, all the way to silicates or iron, okay, which can condense in very hot Jupiter gas giants exoplanets. So multiple species can condense, and we expect very diverse, okay, cloud species. I'm not talking about chemical hazes yet. I'm just talking about condensed clouds. We already got a lot of candidates, right? So it could be very, very diverse. Okay, this is the first take-home message. And we're going to dive into several examples here and talking about the details of those clouds and their roles in shaping the climates. And give you another view of this, okay? This is from Sauerhurst, and usually condensed clouds depends on the temperature, right? If you are cold enough, you can condense water, ammonia. If you're not that cold, you can only condense maybe alkali metals or silicate. I'm talking about a temperature ranging from 100 Kelvin all the way to 2000 Kelvin, right? And in terms of different planets, and we have For example, sulfuric acid clouds on Venus, covering almost the entire planet. And we have our old friend water clouds on Earth with a lot of photochemical phases, which we call smog. And on Mars, we have water clouds, water ice clouds, and sometimes carbon dioxide clouds, the dry ice clouds. And we have a lot of dust lifting from the surface. So Mars dust storms and ice clouds playing a role in early Mars. A lot of interesting things. We're not going to talk about Mars, it's a separate topic, but a lot of interesting things going on there. Jupiter, Saturn, Uranus, Neptune, they are hydrogen dominant atmospheres. They have a bunch of like water, ammonia, or maybe ammonia sulfide clouds and hydrogen sulfide clouds. There are a lot of this kind of stuff. And the Titan, Triton, Pluto, and nitrogen-rich methane CO atmospheres. They have a lot of interesting ion chemistry and photochemistry going on. Hydrocarbon chemistry produce a lot of interesting photochemical phases. Okay, and exoplanets. We know very little about them, but current data already give us strong evidence. What we have clouds on those atmospheres. Okay, so we're also going to talk about exoplanets and what kind of evidence we have and what kind of ways we're trying to explain or interpret the observational data. All right, so today I have an ambitious plan. I plan to talk about, basically showcase 4 examples about different roles of cloud and hazes. How do they form and why do we care about them on planets? Okay, first one will be our old friend Venus, sister planet. And then I will jump directly into the outer solar system to talk about icy bodies. Okay, Pluto, Triton, and Titan, talking about the roles of photochemical phases. And then I will jump even outer the solar system, talking about exoplanets. It's a very rapidly growing field right now. And then I come back to talk about Jupiter and talk about the importance of clouds in shaping the dynamics and banded structures of clouds in Jupiter's atmosphere. So hopefully I can finish all 4 categories, but because they're so diverse, I will focus more in breadth instead of depth. Okay, and so a lot of them I will just showcase several examples and talk about important topics. How hopefully that will motivate you to think about deeply what's going on there or find some interesting topics to study in the future. All right, let's talk about Venus. We all know Venus is very, very bright, right? In the morning and in the evening. And the reason we all know that is because Venus covered by sulfuric acid clouds. Okay, by sulfuric acid clouds, very bright. Thus, bound albedo is 76%. Okay, it's a lot, and it's very bright. So the first question would be, why Venus is so bright, right? And the reason is because this kind of acid actually photochemically produced from the top. Okay, so they produce everywhere, get transported everywhere. Okay, it's covering the entire planet. You don't see that on Earth because Earth clouds are basically dredged up from below, right? You get water vapor dredged up below, and you form discrete clouds, right? In Earth atmosphere. Of course, dynamics play a role. There are a lot of interesting things going on, but the first thing is the clouds formation on Earth and cloud formation on Venus are actually pretty different. Okay. We do have some sulfuric acid cloud layer on Earth. If you're more familiar with Earth atmosphere, you might have heard about the younger layer. In the lower stratosphere, here is the younger layer, okay? But the particle concentration is much, much less, okay, than the particle concentration we found on Venus, okay? And here, the right-hand side is from the Pioneer Venus data. And we have a probe, and we can basically got the profile of the mass loading and the major acidity of the cloud. And also because we have a lot of water on Earth, the sulfuric acid cloud on Earth, or sulfuric acid aerosols layer on cloud on Earth, the lower stratosphere, is pretty dilute, okay? And our Venus is very concentrated, okay, very acidic. That actually pretty interesting when we talk about the implications of habitability of the clouds. And we might need to know the acidity, right? And how, what kind of role they play in astrobiology, okay? And another thing is younger layer, although it's very little, right? It looks like pretty thin in the lower stratosphere of Earth, but people have already thought about, maybe you can use this kind of lower stratosphere layer to reflect or scatter more light out from Earth to cool down the entire surface to solve the global warming problem, right? So this is something you can think about in terms of geoengineering. You perhaps have heard about that, how do we solve this climate problem by injecting some seeds to form more bright aerosols in the lower stratosphere. Something to do with the sulfur here, but sulfur may not be the best candidate for sure. Anyway, if we compare Earth and Venus, the two main differences between the water cloud formation on Earth and sulfuric acid cloud formation on Venus is the first one. Earth water formation, water cloud formation, is you have water vapor dredged up from the bottom, from the ocean, right? And you form clouds by condensation. But on Venus, as I'm going to show you the sulfur cycle. Okay, the sulfuric acid form in the upper atmosphere actually. Okay, above the clouds, and they form in the upper atmosphere, and then they form clouds there, and cloud droplets sink down. Okay, this is only part of the story. Also, you also got a water condensation from bottom of Venus. So Venus is actually pretty complicated. Okay, and the second thing is Venus is a concentrated sulfuric acid. Okay, so it's not pure water, right? And the thing here is it's a binary condensation. Okay, and the sulfuric acid and water, they try to condense together, and the saturation vapor pressure of each species strongly, very strongly depends on the acidity of the atmosphere. So of the cloud droplets. So you can think about they play with each other, because once you change your acidity, you will change your saturation vapor pressure, change your condensation rate, and change your acidity. Right? So they play with each other, very complicated system. So it's not easy to understand this, okay? And as I said, the sulfur cycle on Venus, if you haven't known much about Venus, I give you a very brief introduction here. Venus is basically the sulfur factory. It's carbon dioxide atmosphere with a sulfur species, large amount of sulfur species, OCS, SO2, and those species in the lower atmosphere. Okay, and they are dredged up. Okay, transported upward above the cloud layer where they can meet the photons from the star, and then photochemistry going on, and SO2 will be decomposed into sulfur monoxide, and the sulfur monoxide and will combine and oxygen, and sulfur monoxide, sulfur dioxide, oxygen will combine form sulfur trioxide and emit water vapor and form sulfuric acid vapor, and once you meet cold temperature, sulfuric acid will condense, and water will condense as well. Okay, if you don't have a sulfuric acid, water won't condense on Venus, but because you have a sulfuric acid, you change the acidity of the droplet, so water saturation vapor pressure drops so rapidly, and water can start to condense. Okay, and so a lot of interesting interaction here. And then the sulfuric acid will sink down and evaporate and back into a cloud. This is a very simple picture of the sulfur cycle. Okay, and people used to use very complicated what we call the microphysical model to understand the formation of sulfuric acid cloud. For example, this is from Peter Gao and me. In 2014, we built a model like this and trying to understand the formation of the Venus clouds from 47 kilometers the lower haze layer, and then to the middle layer, and then to the upper atmosphere to explain the upper haze layer observed by Vedic Express. It's very complicated, including nucleation, condensation, evaporation, coagulation, transport, everything there. So we can nicely explain, for example, the particle number density measured by the probe from Pioneer Venus, and even the particle distributions. We have several modes of those particles from Pioneer Venus. So we can explain those, but so complicated. And recently I got a smart student from China and Longkang Dai from Sun University, and he came up with this idea. We actually could explain all of the observations without microphysics. Of course, we cannot explain the particle size distribution, but without that, you can explain the sulfuric acid vapor mixing ratio. You can explain the water vapor mixing ratio. You can explain cloud mass loading. You can explain cloud acidity. And you can even explain the mean particle size. I'm not guiding you through all of the panels here, but just try to show you the comparison between our model and the data we have so far. Okay, very simple model way without microphysics is actually working for Venus. Okay, so it looks to me, this model has captured some essential physics here and can be used to, for example, coupled with general circulation models or complicated chemical models, or used to diagnose the details of the sulfur and water cycle in the atmosphere. And we predict the sulfuric acid should be supersaturated by 1 or 2 orders of magnitude in the upper atmosphere of Venus. And well, right now our detecting upper limit is still pretty high. We need to pin down the detection limit and trying to see if sulfuric acid is indeed supersaturated or not to validate the model. And the second thing is you can see the water vapor has not been measured carefully inside the cloud layer, which cannot, which is not very useful to constrain our model. And hopefully the future observers can help to constrain the water vapor inside the cloud. This is super, super important, I would say. And because that will tell us what is the acidity of the cloud inside these layers, and acidity is not well measured right now. But anyway, this model works, and we can use that to understand the cycles. So this is pretty good. And the cycles, what we found is that basically big cycles and small cycles. For example, sulfuric acid, and you have a big cycle, you form sulfuric acid on top, you sink down and evaporate in the bottom. But most of the evaporated sulfuric acid will be very quickly recycled inside the lower layer, lower cloud layer, and back to the clouds. So the Venus clouds, lower clouds, are actually caused not by the photochemistry, but by this evaporation and condensation rate cycle. This cycle is roughly an order of magnitude stronger than the photochemical sulfur cycle. So the cloud mass is actually dominated by the small cycle instead of the big cycle. And water is different. The water, you have a lot of water from the deep atmosphere and come up, and water actually evaporate before they actually sink down. So you have a small cycle of water and in the upper cloud instead of the lower cloud. That can part of explain why the acidity actually increases dramatically as you go deeper. Okay, so there are a lot of interesting things we can think about, even think about this kind of simple model to understand what's going on there. But this is not the end of the story. And there are a lot of interesting things in Venus and atmosphere. Why do we care about this? Okay, it's because clouds play important roles to shape the abundances. For example, and my student covered Pearson and me, we published a paper last year, and we think the sulfur dioxide is very hard to explain. Okay, the reason is you do have a very large amount of sulfur dioxide below the clouds, but you have a very little sulfur dioxide above the clouds. There must be something inside the clouds eating the sulfur dioxide. And we don't know what kind of thing it is, because the clouds are acidic and the sulfur dioxide really cannot be absorbed inside the droplets, and what kind of chemistry you have there. So this is a very big question, and we have such a big fundamental question sitting in front of us, and we don't know the answer. And some very interesting proposal just came out this year, and Paul Riemer proposed that the clouds may not be that acidic as you thought, and if you have some salts coming, whatever salts from, and you can have hydrated sulfides and sulfates inside clouds, and the acidity will be dramatically lower. And in that case, you can absorb a lot of SO2, explain this. Of course, that is a very different picture that tells us actually the clouds, especially lower clouds of the Venus, is not made of sulfuric acid. It is actually made of hydrated sulfides and sulfates. Okay, so this is a big assumption or big hypothesis, and I hope future Venus mission. We do have future Venus missions. Okay, one from Europe and two from the US, and maybe they can tell us what's going on there. And the second thing is the gas and clouds interaction. The mesosphere might be very interesting, and one of the interesting thing here is if you're monitoring the cloud top species, for example, sulfur dioxide and water vapor above the clouds, and from the last decade, you see there seems the anti-correlation trend, the water vapor decreasing and the sulfur dioxide increasing. They all have very big fluctuations for sure, but in general, they might have this kind of anti-correlation. Looks pretty strong, okay, trend. If this is true, okay, how do we explain that? My student Wenchen Xiao has published a paper last year to talk about, okay, because of sulfur chemistry and water, they trying to eat each other, they compete with each other. So naturally, you can explain if your sulfur dioxide increases, your water will decrease a little bit. But from our cloud point of view, we think another interesting mechanism could be proposed. For example, if you have more sulfur, you will form more clouds. Well, if you form more sulfur gas cloud, they will absorb more water, right? So there will also cause some kind of anti-correlation. So there are a lot of interesting things. Okay, I'm not going to spend time to talk about another interesting thing. It's about sulfuric acid. It's about a sulfur dioxide, which seems increasing with altitude, okay, from Venus Express observations. And we think there's a source in the upper atmosphere, and the most probable source, in my mind, as we predicted or proposed a long time ago, it could be sulfur haze, okay? And we're still waiting for the observational evidence. So there are a lot of interesting things. Finally, why do we care about Venus? I think it's an interesting thing to think about habitability. I didn't spend any time to talk about the first thing inside the clouds of Venus, which I bet you have heard about it. And of course, how do we, well, it's under debate, okay? It's very interesting and motivating future studies for sure. But from clouds point of view, if the clouds are really acidic, as what we predicted from our model, as I said, you really need to measure the water vapor to constrain the acidity. And anyway, from our simulated water vapor, and we found this paper from Houseworth, and talking about if you search on Earth and you find extreme files, and they cannot really live in very acidic environment. Of course, the limit right now we found out is about 0.5 in terms of water activity. Basically, it's water divided by the super saturation, the saturation vapor pressure, and the maximum the water activity is about 0.03. Okay, it's far below. Okay, so it looks like if the acidity is so acidic, right? The clouds are so acidic, you perhaps won't have a very normal habitable environment for those microbes to survive. But if Paul Riemer is correct, the clouds are actually much less acidic than what we thought. It would be interesting to see if the clouds are more friendly for the microbes. So there are a lot of interesting things we should think about clouds on Venus. Okay, let's move ahead, and also want to talk about the outer solar system, talking about hydrocarbon hazes and ices, icy bodies. Now we're changing our mind, and we are thinking about the nitrogen, methane, CO atmosphere. Okay, Pluto, Triton, okay, Moon, Neptune's moon Triton, and the Saturn's moon Titan. They are all nitrogen, methane atmospheres with a lot of CO on Pluto's and in Pluto's atmosphere and Triton's atmosphere. So you have a lot of photochemistry and non-chemistry coming that produce hazes. Okay, and they're also very cold because of the outer solar system, right? So hydrocarbon and nitrile ices will condense in the atmosphere. So it's very interesting. Well, first, when we thought about the Pluto haze formation, I'm going to show you the New Horizons discovered like numerous haze layers, and you can see from this picture here, right? This is backlit, and this blue ring you see here is from the radius scattering from little particles in the Pluto's atmosphere. So there are a lot of hazes. Okay, even Pluto's atmosphere is only 1 Pascal. It actually has a lot of hazes. Originally, we just said, okay, Titan has a lot of photochemical haze. Maybe we should also have similar photochemical haze on Pluto. So maybe those particles are photochemical hazes. Okay, part of it's true, but now we think about different story now. Okay, the reason is we also found out the Pluto's atmosphere is much colder than what we thought. Okay, what we thought is a warmer atmosphere, now is colder atmosphere. So maybe we should think about different way of haze formation on Pluto. On Titan, we think about you produce this kind of hydrocarbon haze in the upper atmosphere, sink down. And so this is what we usually thought, okay, from Peter Gauss' paper in 2017, and we form those kind of aggregated particles. And this something you can find out from secondary organic aerosols from Earth. But now the new paper came out this year from Pinayotis Navas, and think about, no, maybe we should think about ice formation in Pluto's atmosphere. Maybe those haze particles are basically ices. Okay, the reason is so cold. They're so cold, and so when you form those kind of gases, you know, and these gases can directly condense, okay, on seeds. So you don't really think about, you know, like Titan haze formation, but you think about ice cloud formation thing like this. All right. So what's the difference between the two, right? And from Lavas et al., the composition will look very different, right? And ice, you have to think about what kind of ice is that. And his model predicted you have a lot of hydrogen cyanide ice. Okay, HCN ice is our old friend because we also found some HCN ice on Titan, but not that much. Okay, but here on Pluto, it predicted over-dominated the haze layer, the particle layer above 400 kilometers. Below that, you have hydrocarbon ices. Okay, the one very important one is C4H2. Okay, which is something we didn't imagine at all before. Okay, but his model predicted. Compared with ice and Titan's normal haze layer, Titan's haze you see it looks orange ball and those kind of stuff, right? It's very absorbing in the visible, but the ice could be pretty reflective. So very different energy manipulation in the atmosphere, right? And the second thing is ice is different from hazes. Hazes can emit in the continuum in the infrared, but ices can only emit in the vibrational rotational bands, right? And so they have very different thermal infrared opacities, but does not necessarily mean the ices can emit less. Okay, the HCN is actually pretty strong emitter in the far infrared. That can efficiently cool the atmosphere down. I'm going to show you one example on Pluto. This is actually pretty important. So Pluto, Triton is even colder than Pluto. So Triton and Pluto, perhaps you have ice condensation instead of like normal haze formation on Titan. And this is my postdoc, Kazumasa Ono, and he published a paper this year talking about on Triton, Neptune's moon Triton, and we also we have to include ice condensation in order to explain the Voyager data. Otherwise, there's no way you can explain that. Okay, so the ice condensation is very important. And how do you form ice on top of those particles? Okay, depends on a lot of interesting things. Supersaturation of the vapor, surface tension, and a lot of interesting things inside Earth. You know, this is something we even don't know for the ice cloud formation on Earth. So it's really the frontier. And but a lot of interesting things could go on. And my postdoc Xinting Yu is leading a group of undergrads in UC Santa Cruz and trying to characterize the supersaturation and surface energy. You know, they lab mirror contact angle so they can get mechanical properties. A lot of this kind of stuff can be used to infer the existence of cloud formation. Okay, for example, if you have very different, you have very high surface tension, and or you have very low surface tension, or the average surface tension, and you calculate the contact between the particles, the floating particles forming the tight dense atmosphere, and the ice condensation. For example, the HCN ice or methane ice, methane liquid in the troposphere, or ethane ice in the polar region. And you can predict what kind of clouds could form on Titan. And what we found is, there are several important clouds we can find. Some of them have been observed, some of them have not been observed. So we need to predict. But just to give you the example, okay, in order to understand what kind of ice can condense, we need to understand the properties, the microscopic properties of the seed and the interaction with the vapor. Okay, let's give you an example and why we care about those particles. The care about the particles because the particles can explain the temperature of Pluto. This is actually very, very interesting. We never expected that. As I said, Pluto is much colder than what we expected. Okay, there are two curves. The observational curve is black, and the blue curve, the observational curve is black, and the pre-encounter model curve, before we send out the New Horizons mission, is blue. And you can see the observed value is 30 Kelvin colder than the model, than the expected value. And so obviously you need a coolant. And if you search all of the gases we mirrored and you try that in your radiative transfer model, and you found out there's no way you can explain it. Okay. And what we proposed is those icy hazes. Well, we originally proposed hazes. Now, because we know it's ice and we try icy hazes, so those icy hazes should control the atmosphere radiative balance, okay, on Pluto. And this is a work from my student Lincoln Wan, and we found out because on Pluto you have really abundant haze, and they can absorb the solar flux. Unless the albedo is exactly 1, okay, you should be able to absorb more solar flux than methane gas. So the heating rate is actually important, but also the infrared cooling rate from those ices are also important. So both balance each other and overcome the gas radiation. So this is a very unique atmosphere. Pluto's atmosphere seems the energy balance is dominated by particles instead of gas. Okay, totally dominated by particles instead of gas. So this is a very interesting atmosphere. We never saw this kind of stuff before. Okay, so once we go out in the outer solar system, we found something new. Anyway, how do you tell if what kind of ice is there and if it's Titan-like haze? We can simulate the thermal emission from the Pluto's atmosphere and using James Webb Telescope. JWST, fingers crossed, will be launched very soon this year. And so you can see the ices have peaks, bumps, and the hazes have continuum here. So by looking at JWST data spectra, okay, from the medium infrared, we can know, okay, what kind of ices in the atmosphere and what kind of importance of their energy budget balance by these ices. And also, one interesting thing to think about this is you can have clouds and hazes interacting with surface liquid. This is something very crazy story. Okay, you have a lot of particles from the Titan's atmosphere sink down, right? And they can interact with the lakes in the polar region. And one very interesting hypothesis in 2019 is those particles can float on top of the lakes. And because you think about oil field, right? On top of the lakes, so you can depth waves, right? You can depth waves. And indeed, from Cassini radar observations, so we found out the wave amplitude on Titan Lake seems extremely low, okay? So it's a big puzzle. And this hypothesis said, okay, maybe you have those particles, you know, you just got a field. And so depth waves. It's a very interesting hypothesis. My postdoc Xinting is trying to understand the details of this. And what she found out is if the particles are heavier than the liquid is hydrocarbon lake, okay, it's pretty light. And there's no way you can do that, okay, because they're pretty wetting, okay, with the liquid. Okay, the contact will very quickly becomes zero. So it will be sink into the bottom of the lake, okay. Only if those particles are actually lighter, okay, density is lower than the liquid, it can actually float. Okay, so we are thinking about something very microscopic, right? We're not just think about if it's lighter, it will float, if it's heavier, it will sink, but also think about the interaction between particles and liquids. Okay, what is the mechanic force between them? And so by mirroring those kind of stuff from the lab, and Xinting confirmed that if you have a very fluffy, very low dense, like cotton ball like, right? And those kind of particles, you can float. Otherwise, you will sink down into the bottom. Okay, so very interesting things.
So, we have about maybe 7 minutes left. We could take a few questions.
Yeah. I think I definitely have a lot of materials to cover. So in the end, I will basically talk about something I really want to talk about in 7 minutes, and the mineral and metal clouds on hot planets. Okay, so when we go beyond the solar system, we have found diverse exoplanets, ranging from very cold exoplanets to very hot exoplanets. And so we expect something else, you know, than the solar system atmosphere clouds will occur on those planets. And we do find evidences. The evidence comes from the transmission spectra, okay? The idea here is you have exoplanet transit in front. It's like a solar eclipse, right? And you have planet transit in front of their host star. You can do the transmission spectroscopy measurement. And in the near infrared, here is water band. You can see, you know, we predict how much water is there from thermodynamics, and if you didn't see this kind of water features, you see very flat spectra, you know there is something there. And indeed, from our current about like 40 samples, okay, there are 40 planets, and we found there's a trend, very interesting trend. And you have some planets with very clear water amplitude, some planets with almost no water amplitude. And one of the very strong implication is you have clouds suspended in the upper atmosphere, blocking the water emission, water absorption lines. So you do not see those water features. So idea here is showing the cartoon, right? You have a steroid coming in the clear atmosphere, you will see those kind of spectra of the gases. But if you have clouds, you are blocking, and you will show very different spectra. And what kind of clouds are there? They are definitely not water clouds. We're talking about something above 1,000 Kelvin, right? We're talking about something almost like 2,000 Kelvin. And so there's no other choice, basically. Okay, not one choice is you have chemical hazes. The other choice is basically you have those kind of rock and metal clouds. And those clouds can condense, okay? They will be the vapor phase in the bottom because hot enough. And they bridge it upward, meeting the cold temperature in the upper atmosphere, they will condense in the atmosphere. And what kind of clouds look like this? These are minerals, right? And titanium sulfur, titanium oxides, iron clouds. silicates, aluminum oxides, all of those kind of stuff. And so we created one of the first microphysical models by my student Diana Powell, and she just graduated this year and is a postdoc in Harvard, and she's going to be assistant professor in University of Chicago 2 years later. And she built this silicate cloud formation model for hot Jupiters and trying to use titanium oxides as a seed to condense silicate vapor on that. And what she found out is clouds have very strong impact on the transit spectra. Okay, so this is important, very important for exoplanet observations in the future, especially in the JWST period. And for example, you can see this gray line here. It's a clear atmosphere transmission spectra, but once you got clouds, right, you see muted and sloped optical spectra. You have sometimes bumps of silicate, sometimes you have clear windows. Maybe you can probe down into deep atmosphere, and the atmosphere show very different temperature and cloud structures between the west limb and east limb and the polar region. Okay, so this is very important for future observations. And recently also we found out the statistical trend of cloudiness. The idea is to measure how much of the water amplitude, water infrared band amplitude got muted, right? And then you can think about use that as a proxy of how cloudy the atmosphere is, and print them as a function of equilibrium temperature. And found out there is something like sink down, emerge, and has a curve here. We do not know exactly what's going on. Some hypotheses and published paper on this. Some related to chemical hazes, some related to silicate condensation, and the data not good enough to give us a very precise shape of this cloudiness trend. But this is emerging. And I said, this is not a random thing. It looks like exoplanets, we can use statistical methods, understand there is something fundamental going on these planets. Of course, the haze part is also puzzling. Okay, in this part, you don't expect silicate condensation, but chemical hazes. So I will use my last slide here to motivate people doing lab experiments. Okay, already the Sarah Hurst lab in the US is doing this, trying different temperature, different combinations of gases in the atmosphere, and trying to form hazes. And you can see this is real sample images. You can see dark, orange, white, very different production rate, very different composition, very different cohesiveness, and very different spectrum of passing. So I will stop here. I think we have enough to discuss. Okay, so I really hope if someone wants to simulate a haze in their lab and to help us to characterize the extreme diversity of the clouds and hazes, both in the solar system and outside the solar system. All right, so I will stop here and thank you for your attention, and I will take your questions.